So we have the square root of 98. What I mean by simplify the radical is that I would like to have, the smallest possible number underneath the square root symbol, and if at all possible, for me to factor out any perfect squares that might exist in the problem. And so, like for instance here, the square root of 98, I can factor into two different radicals, and that's the same thing as having the square root of 49 times the square root of 2. Because again, it's based off those exponent rules that if I have two bases raised to the same power, I can multiply the two bases together and keep the power. And a square root is just a 1/2 power, so I can keep the root along with them. So this is an extension of that, some of those exponent rules you saw on the previous page. Now, the reason why I separated into these two is that I looked to see I looked for the biggest possible perfect square that would factor out of 98, and 49 is that biggest perfect square. Remember, it's the only perfect square really. But sometimes, I mean, you might have a situation where a number has, several perfect squares that'll factor out of it. You want to pick the biggest one that you can get. And even if you don't pick the biggest one, what you end up with is a radical that still has perfect squares going to be factored out of it, and therefore you should need to keep going until you get that all taken care of. But since I can separate it like this, well, I can actually take the square root of 49 and say that's 7. And therefore, this answer, when it's simplified, is 7 times the square root of 2. I'm not changing the value of anything. If you do the square root of 98 on your calculator or do 7 times square root of 2, you get the exact same decimal. It's just like for purposes of maybe combining some like terms later or doing some calculations beyond this. Sometimes it's a little easier when you have smaller numbers involved. So it's a good idea to sometimes look to see if this can happen. The cube root of 20 times the cube root of 4. Now here, 20 and 4, neither one of them are perfect cubes. However, if I put them together and do the cube root of 80, because again, if I have two different bases raised to the same power, technically these are both raised to the 1/3 power because that's what the cube root would be, I would end up with the cube root of their product. 80 is not a perfect cube in and of itself either, but a perfect cube does factor out of it. 8 is a perfect cube. Now, obviously, as you go through and do these things, you have to sort of make yourself become aware of what some perfect squares are, what some perfect cubes are, maybe what some perfect fourth power and fifth powers are. We don't usually get too far beyond that unless you're talking about twos and threes, that kind of thing. But 8 is a perfect cube. So when I split up in a very similar manner I did in part A, I can now say this is 2 cube root 10. And the reason why we also might want to keep it like this, these are exact answers. I'm not rounding anything. And if I get this as my answer at the end and then want to get an idea of approximately what it equals, then I can just put that in my calculator, get an answer, and round it off once. Whereas if I'm doing, if I get this early on in a problem and then there's other things they want me to do to it, and I'm rounding off each and every time I do it, that's going to cause me to keep rounding and rounding and rounding. And it actually, in many cases, depending on how many more steps you have to do, can actually move you far enough away from the right answer to say, okay, is this the right answer or not? The square root of 32 plus the square root of 8. Now, it says simplify. Now, anytime you're given an addition problem that says simplify, you're going to probably be carrying through that addition. Okay? Just right now, if we're kind of treated as we do with some other algebraic phenomenon, the square root of 32 plus the square root of 8, they're not common radicals. I would not be able to add them together as they are. But because we're asked to simplify, it's a very rare circumstance, and so rare that on a quiz or a test you would never be asked to simplify anything that could not be simplified any further. This addition should be able to be carried through. I should be able to get a more simplistic answer. So, the 32 I could factor into square root of 16 times square root 2, and the square root of 8 I could factor into square root 4 times square root 2. Much of this very similar procedure as I did for part A. Which means I have 4 times the square root of 2 plus 2 times the square root of 2. Now I have a common radical between my two terms. And so 4 square root 2's plus 2 square root 2's gives me 6 square root 2's, and that would be my simplified answer. It would be the exact same value as if you would plug in the square root of 32 plus the square root of 8 on your calculator. You might have to use some parentheses depending on how old your calculator is. And if you plugged in 6 times the square root of 2, you should get the exact same decimal values. I mean, so yeah, that's one way to check them for the time being. When you have the calculators, make use of them. Okay, check your work. This one here, I didn't even bother with any particular slide advancement or transitions here. I'm just kind of showing how this problem would be worked through. And this is not the only way to do the problem. It's not the only way where you would end the problem. It really depends on directions you're given. Um, you're given this initial expression, and it says to simplify the expression and use positive exponents only. And generally, that's what we're going to always want to do. We always want to have positive exponents, and that's what's going to determine ultimately what goes on the top or bottom of a fraction bar when you have expressions that involve different powers. Because remember, negatives mean do a reciprocal, and therefore, if you see a negative on something that's being raised to a power, it's on top. You want to move that to the bottom to get rid of the negative exponent to make it a positive one, and vice versa, for that matter. So here, what you see me do is the first I distribute. I take care of all the negative exponents. So I mean, I take the 2x and raise each part to negative 2 power. I take 16y and raise each part to the 3 halves power, so forth and so on. And then what I try to do is see if there's anything that some commonalities between them. See if I can put them in terms of like different powers and things like that. So what you see me do first is I take all the numbers and put them first. So like the 2 to the negative 2, the 5 to the 4th, the 16 to the 3 halves, which does become 64. I put on top first, and I put the letters with the exponents next. And I do the same thing on the bottom. I put the 2 to the negative 5, the 5 squared. And you notice I'm also trying to line them up so that I can carry through some cancellations. And I'm also going to line up the x's, y's, and z's to do the same thing. So what happens is, if I do 2 to the negative 2 power divided by 2 to the negative 5 power, when I divide two powers of the same base, in this case they both had a base of 2, I subtract the exponents. So negative 2 minus negative 5 would be 3. The same thing with the powers of 5. 5 to the 4th divided by 5 squared. When I divide those two powers of 5, I subtract the exponents. 4 minus 2 is 2. 64 divided by 2 is just 32. And I do the same thing with the x, y's, and z's. X to the negative 2 divided by x to the 1 half. Again, I'm going to subtract the exponents. Negative 2 minus a half is negative 2.5 or negative 5 halves, writing as a single fraction. Y to the 3 halves divided by y to the second. Again, I subtract the exponents. 3 halves minus 2. It has to be in that order. The one that's on top and the one that's on minus 1 on the bottom gives me a negative 1 half. And of course, z to the 4th divided by z to the negative 5 means I'm going to take the exponents of 4, subtract negative 5 from it to get z to the 9th. And now I work on doing some more simplification. So 2 cubed is 8, 5 squared is 25, 32 is still 32. I move the x and the y to the bottom to get rid of the negatives on their exponents, so the z to the 9th still stays on top. So the top becomes 6400 z to the 9th. I could have left the x to the 5 halves and y to the 1 half down there. It really depends on the question being asked. I mean, that's a satisfactory answer because it says simplified. It is a little bit more simplified. With the x to the 5 halves, y to the 1 half, even if I had underneath the 6400 z to the 9th. But I can also realize that both of them have a denominator of 2. They're both being raised to the 1 half power, which means their product is going to be being square rooted. Again, that depends on the situation though, because some textbooks and some mathematicians or whoever you're talking about a given day, week, or whatever wouldn't consider a situation where I have a radical in the denominator to be a situation where I would say it's simplified, because radicals in the denominator is something they don't usually like. They usually want that rationalized. These would be acceptable answers to me, but you may have other professors or things like that say, okay, we have to do another step now. We have to multiply the top and bottom by the square root of xy.